Hello again, everyone. So in the previous two videos, we focused on Lewis dot structures and the power of their prediction with regards to ionic compounds, those compounds that have a metal and a nonmetal. And we were able to use the Lewis dot structure for that metal and nonmetal, along with the octet rule, to be able to predict formulas for those compounds. So for example, with KCl, we were able to predict that a molecule of KCl would be 1 potassium and 1 chlorine, because with that Lewis dot structure of potassium, it would love to completely donate that electron to chlorine, thereby giving chlorine 8 outer electrons, valence electrons, satisfying an octet, along with potassium losing that electron to then have the same number of electrons as argon. And so we talked about how those Lewis dot structures, along with the octet rule, can help correctly predict ionic compounds. We can do the same with covalent molecules or molecular compounds. Those are molecules that involve 2 or more nonmetals. In this course, we're primarily going to focus on molecular compounds that just have 2 nonmetals in them. But we can use those Lewis dot structures in a similar way, remembering though that in molecular or covalent compounds, those electrons are not donated, they are shared. Okay? So if I wanted to try and use Lewis dot structure in tandem with the octet rule to say something about the predicted formula for a covalent molecule, I could do that. So let's say I wanted to predict what the molecular formula for water would be. Everyone knows that that's H2O, but how can we predict that from these Lewis dot structures? So I have written here the Lewis dot structure for hydrogen. It's in group 1, so it has 1 valence electron. Here is the Lewis dot structure for oxygen. And you can see that oxygen would love to have 2 more electrons, to have 8 in its outer shell. And hydrogen, along with helium, those are 2 exceptions to the octet rule. They don't want 8 valence electrons, they want 2, they want a duet. So hydrogen really doesn't want to donate its electrons. It would rather keep it and maybe share with oxygen. So in particular, you could envision 2 separate hydrogen atoms coming to share their 1 valence electron with an oxygen atom to give you H2O. Yeah. So with those Lewis dot structures of the individual atoms, along with the octet rule, which is that atoms want to beg, borrow, steal, do whatever they can to get 8 valence electrons. With the exception of hydrogen and helium, they want 2. We can predict what molecular formulas are using these Lewis dot structures. So we're going to do many more examples, but I want to introduce a few more terms to you, and then we'll use those terms in describing some molecularly based Lewis dot structures in the next video. So as I showed on the previous slide, this is the Lewis dot structure for hydrogen or for water, and it clearly shows each of the valence electrons that are associated in that structure. So valence electrons that are in between 2 atoms, ones that are in between 2 atoms, the ones that are shared between atoms, are written as bonds. So this form of Lewis dot structure can also be written like this, with those shared electrons written as single bonds. Okay. Electrons that are not shared between 2 atoms, or not in between the space between 2 atoms, are called lone pairs. Okay. So in this H2O molecule, we would say that water, specifically the oxygen on that water, has 2 lone pairs. They're shown here in the upper right. They're also shown a little more explicitly here on this lower right formula, along with the bonded pairs of electrons between the bonded atoms. So these terms of bonded pairs, lone pairs, are going to be important because you're going to need to look at a Lewis dot structure and say something about how many lone pairs of electrons are on the central atom and how many bonded pairs are attached to the central atom. And it's also going to be important to know if electrons are bonded or lone pairs, because when you count electrons to determine if the octet rule is satisfied, the ones that are in between the spaces between the two atoms are counted as equally shared. So for example, the electrons that are in between the hydrogen and oxygen that form that single bond, they contribute both to the octet of the central atom, but also to the hydrogen's duet. Okay? So, these terms, lone pairs, bonded pairs, octets, duets, we're going to be using them quite frequently in the rest of this chapter. In the next video, I've got some sample Lewis dot structures written, and then we're going to look at those Lewis dot structures and using these terms be able to say something about the bonded pairs and the lone pairs associated with the central atom.